Good afternoon, everybody. Today we are discussing the next topic, that is chiral reagent controlled asymmetric synthesis. So, as the name stated, the chiral reagent controlled asymmetric synthesis means here the starting material is an optically inactive compound, but the reagent is an optically active compound. Sometimes the reagent may attach to a bulky group like chiral auxiliary, and this will work as a reagent in the asymmetric synthesis. So consider the reduction of a ketone. So in the reduction, for example, in the ketone is an optically inactive compound, but due to the reduction, we are creating an additional chiral center. But if our reducing agent is lithium aluminum hydride, it has no selectivity. So you know that the carbonyl group is a sp2 hybridization, and it is a planar structure. So the lithium aluminum hydride can approach the carbonyl site from both sides, either top or the bottom. So there is no selectivity and we will get a racemic mixture. So that's why this is the general reduction I have shown here. The starting material is a ketone, and if you are treating with lithium aluminum hydride, lithium aluminum hydride has a complex structure, and Li act as a plus and AlH3 act as a minus, and it will form a interaction and we will get a racemic mixture. But if you are using a chiral reagent, and binol is an example for the chiral reagent. Binol means it is a biphenyl instead of the lithium aluminum hydride. Lithium aluminum hydride is a normal reducing agent. If you are replacing two of the hydrogen atom in the lithium aluminum hydride, and if you are connecting the aluminum atom by using a diphenyl, then that reducing agent is a optically active compound, and usually for reduction, optically active reduction, we are using binol and the structure of the binol is very important. There are two structures, there are two configurations for the binol. One is R binol H, and the remaining one is the S binol H. So only the difference between R and S is the in the R binol H, one side I have shown by the darkened, and this darkened side is towards the observer and the other side is away from the observer. So in the S, the darkened side is different. That is the only difference between R and S, and it is acting as a chiral reducing agent. And how we will do the asymmetric reduction? By using binol H. See here, in the binol H is react with the carbonyl group like this. I have shown the reaction. So Al minus is reacting with the carbonyl group, carbon side, the carbon of the carbonyl group, and hydrogen is connected to that carbon. Okay, then, and since the diphenyl is a bulky group, the binol can approach the carbonyl group only through the one side, and since it is passing through a cyclic hexane ring transition state, we have to avoid the 1,3 diaxial interaction also. Okay, so this is the final product. We know that only a single product is formed here, and the configuration of that compound is S. Okay, and the binol which is acting acting as a chiral reagent here. Now, so in the chiral reagent, if you are using the asymmetric reduction by using binol H, we will get the R configuration. See here, in the reduction of the carbonyl compound using R binol H, we will get R configuration. If you are using S binol H, we will get S configuration. And these are the major product, and we will get only single product here. But we can tune the reactivity of the binol by changing the R group. So enantioselectivity for a reaction increases from R is equal to Me. If you are substituting R is equal to Me, we will get 95% R configuration, and if the R is butyl group, then we will get 100% the product. But the product amount decreases for R is equal to ISO or PR. Okay. Now we are moving into the next reducing agent, that is IPC2BH. This is the structure of the IPC2BH, and the name is diisopinocamphile borane. So see here in this structure, we know that the diborane, the molecular formula of the diborane is B2H6, and diborane, that means the diborane is the combination of the two monomer unit of the BH2. So consider one single monomer unit BH2. If we are replacing the two of the hydrogen atom by the camphor, we will get IPC2BH. So what is the structure of the camphor? So this single ring is the structure of the camphor. So we have to study the structure of IPC2BH. Since in IPC2BH, as the name stated, here there is only one hydrogen for the hydration. Okay. Now we will discuss the asymmetric hydroboration using IPC2BH. We know that only one hydrogen atom here. This is the structure of the IPC2BH. This hydrogen is used for the reduction of the alkene. And here we get the hydrogen is substituted in this, and we will get this state. After this, we have to remove this compound, remove the IPC2BH by using hydrogen peroxide. Okay, so the final structure is an alcohol, and this is the structure. And next is the IPCBH2. So here we know that this is the IPCBH. So as we discussed earlier, IPCBH have only one hydrogen for the reduction, whereas in the IPCBH2, so here the monomer BH3, only the one of the hydrogen atom is substituted by isophenyl camphyllyl borane. So the two of the hydrogen is available in IPC2BH for the reduction. So the two substrate can bind to IPC2BH for the reduction. Okay. Now we are moving into now we studied the three reducing agent for the chiral active reducing agent. First one is the binol H, second one IPCBH, and the third one IPCBH2. I hope that you understood the concept. Thank you.